Hello everyone, today we'll talk about the matrix of a linear transformation, material from 1.9. So the idea is that, given a linear transformation, say from Rn to Rm, remember this is just a function, if you like, that eats vectors in Rn and spits them out in Rm, and satisfies two things, right? That the sum of two vectors, if I input that to the transformation, this is the same as taking the sum of the transformation applied to each summand. And the other thing is if I take the scalar of a vector and I apply the transformation, that's the same thing as applying the transformation to the vector and then scaling. We want a formula. And it turns out that we're going to have a pretty good answer for this. And let me do this by example. So we want a formula that kind of tells us what the transformation is. It's a little bit vague, but let me do this, like I said, with an example. E.g., suppose I have a transformation from R2 to R3, and I know that T of E1, so E1 is the same as 1, 0. That's the name. I don't know if we've talked about that before, but E1 is a vector that has a 1 in the first coordinate and zeros everywhere else. And I know, let's say, that this equals, 5 minus 7, 2. And we also know that T of E2, which is by definition, E2 is going to be the vector 0, 1. So it has a 1 in the second coordinate and a 0 everywhere else. Let's say I know that this is minus 3, 8, 0. Okay? I want to know what is T of, an arbitrary vector. So let's say x1, x2. Okay, so, again, all I know is that it sends this vector 1, 0 to this vector in R3. It sends 0, 1 to this vector in R3. Okay, just with that, those two pieces of information, notice what happens. Let's just compute this guy and use linearity. So we know that T of x1, x2, right, how can I write this? So here's kind of a trick that I'm going to use here, is that x1, x2 is the same thing as x1 times the vector 1, 0 plus x2 times the vector 0, 1, right? I mean, just think about this linear combination, just scale this by x1, this by x2, add them together, and you get this. Okay, well, what do we know? This is a linear transformation, so when I see the sum of two things, this is the same as T of x1 times 1, 0 plus T of x2 times 0, 1, right? That's by that first property that it preserves sums. And now I've got each summand, it looks like T of a scalar times a vector. So this is the same as x1 times T of 1, 0 plus x2 times T of 0, 1. I'm just pulling out those scalars. And let me go to the next page here. So what is this? Well, the point is that we know what those two things are, right? We know T of 1, 0 and we know T of 0, 1. So I'm going to just put those in there because I can fit this here. So this is going to be, what is this? This is x1 times 5 minus 7, 2 plus x2 times minus 3, 8, 0. And then, well, finally, what is that? That's going to be, if I want to write this as a single vector, the first entry will be 5x1 minus 3x2 minus 7x1 plus 8x2 is the second entry. The last entry is 2x1 plus 0, right? And so that's my answer. That's going to be the transformation applied to any arbitrary vector. I just take this, in fact, linear combination of the two. Okay, but what is this? This should look familiar, right? So this linear combination is really equal to, so let me write this as a punchline. So T of x1, x2, this is a linear combination of two vectors with weights given by x1 and x2. That's the same thing as saying this matrix, right, times the vector x1, x2. Okay, and call this matrix maybe A. But the punchline is that the transformation applied to a vector is in fact matrix multiplication times that vector, where the matrix is just given by those columns, has columns given by what we knew about these two vectors here, the 1, 0 and the 0, 1. Okay, so what's the punchline? So here's the fact that we basically, more or less proved, but I want to write this down in generality. So suppose t from Rn to Rm is a linear transformation. That's important that it's linear, of course. Then there exists a unique, so one and only one, m by n matrix A, that satisfies, what we just said, that if I take t times a vector x, that's the same thing as a times that vector x. So this is the transformation applied to the vector, and I'm saying that that's just equal to matrix times the vector. So it's matrix multiplication in the end. And that's kind of amazing because you started out with this arbitrary linear combination that I knew nothing about. It turns out that it's always matrix multiplication. And this is for x in Rn, that's the input vector. And in fact, we know what A is. I actually just told you what A is. So A is going to be equal to, so the first column will be t of E1. The second column will be t of E2 up through t of En, right? So if I'm in Rn, I should have n columns to this thing. Okay, and so this is called, this as a name, this is called the standard matrix. For the transformation t, okay? Okay, so that's our main kind of fact for this lecture, that if you give me a linear transformation, I can actually give you a matrix that represents it as matrix multiplication. And let me just recall that, just to write this down, E1 is going to be the vector that has a 1 in the first coordinate, zeros everywhere else, and, however many you need to be in that space. And then the net, E2 would be only a 1 in the second entry, a 0 everywhere else. And En is this one that has zeros everywhere, except in the last entry you've got a 1. Okay, so that's just what I mean by those vectors there. Okay, so let's do maybe an example here. So for example, let's find the standard matrix for the transformation t will go from R2 to R2, where t rotates a vector, let's say by angle theta, in the, let's say, counterclockwise direction. Okay, so what do we have to do? So from above, what we saw is what we need to figure out for this, we just need to figure out what does t of E1 look like. So remember E1 is 1, 0 here, right? And we need to know what t of E2 looks like. So what is this and what is this? After I apply that transformation, what happens when I rotate by theta? So we're going to use a little bit of, maybe high school geometry, or maybe earlier, I don't know when you guys see this. But let's see. So what I do, right, is I say, okay, here's E1, right? E1 is this vector here, 1, 0. And now when I apply t to it, right, it's going to rotate it by whatever theta was. Okay, so this is t of E1, right? Now, let's try to get the coordinates for this guy. So this is where your, I guess, trigonometry more than geometry comes in, right? So if this is a little triangle, let me zoom in on that. Here's this vector, and I've got an angle theta. Now remember, our cosines and our sines. So what is, if this is y and this is x, right, we know that what cosine of theta is adjacent over hypotenuse, right? So this will be y divided, well, what's the length of this guy, right? This has length 1 because it's this vector 1, 0. So cosine will just be adjacent over hypotenuse, which is x over 1. And sine theta, right, is SOHCAHTOA, so that's opposite over hypotenuse. Well, again, this is y divided by 1, so this is y. So in other words, this vector is actually equal to, well, its x-coordinate is cosine theta, and its y-coordinate is sine theta. Okay, so t of E1 is equal to cosine theta sine theta. Well, similarly, let's look at E2. It's going to be a little bit maybe more involved just because we're going to be a little bit off of the kind of standard position of your triangle. But when I apply the transformation, right, this will now be theta here, okay? And this is t of E2, right? Because I took that vector E2, rotated in the counterclockwise direction by theta, okay? So what is this guy? Well, now this, if you think about it, right, this quantity, right, this distance here is the same as the y that I had here, right? Because if you think about taking that triangle, take this triangle, rotate it, and put it in the position over here, this is actually, this distance is y, which we knew was sine theta. And this distance is the same as here, the x value, which we called cosine theta before. So the punchline is that t of E2 is what? Well, the x-coordinate is now sine of theta. Well, be careful, it's not sine of theta because it's in the minus direction. It's actually minus sine theta. And then this, the y-coordinate of this vector is going to be cosine theta. Okay, so in the end, we've got t of E2 is this. So our rule from the previous slide says that, the matrix A is going to be, well, I put t of E1 in the first coordinate, and I put t of E2 in the second coordinate. And so what I have is, well, t of E1 was cosine theta, sine theta, and then t of E2 was minus sine theta, cosine theta. Okay? So, again, theta is the thing that we're rotating by. So, for instance, if theta was, I don't know, pi over 2, right? If you're rotating by, in other words, 90 degrees, right? What do I get? Well, A is going to be, so what's cosine of pi over 2? It's 0. Sine of pi over 2 is 1. Minus sine of theta is minus 1, and this is 0 again. So this is the matrix that rotates by 90 degrees in the counterclockwise direction. Okay? And again, you could now just give me any theta, and it'll tell you the standard matrix for that. So I want you guys to have a look at pages, I think this is 74 through 76 of the text for more examples of interesting, I'll say, 2x2 matrices. So what we saw here is how to rotate by theta degrees. So in your textbook they give you examples of different things you can do. So in terms of reflections, they talk about, let's see, I've got it here, reflections. They also do contractions, what are called shears, and then I think the last thing is going to be projections. So what I'm trying to say here is that, all of these kind of geometric operations turn out to be linear transformations from vectors in the plane to vectors in the plane. And you can, since they're linear transformations, they all have matrices that do it. And, you can imagine this is very, very useful if you're doing, say, computer graphics or, anything where you need to think about an object and rotate it, reflect it, contract it, shearing, which has a meaning I'll let you look up, or projection. So these kind of things that are typical geometric operations have matrices that actually do the work for you. Okay, we'll continue next time. See you then.